This is part 3 of the Chapter 12 homework. Chapter 12, number 56. Talks about a vacuum with a pressure of 10 to the negative 8 torr. Now, first of all, before continuing on this problem, you need to figure out what a torr is. And I realize that's not one that's readily easy to find in the book. But if you're a good physicist, you should be able to find such a conversion, maybe on the internet or wherever. What you should have found is that a torr is equal to 1 millimeter of mercury. Other conversions that will be useful is that 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr. So in problem number 56, it says, what's the number density of air molecules at this pressure, assuming room temperature of 20 degrees Celsius? One thing we need to figure is that, actually let's first do the pressure right here. Figure out what it is in MKS units. So if we have 10 to the negative 8 torr, that gives us, we know that it's 760 torr per 1.013 times 10 to the 5th pascals. So here we have 1.3 times 10 to the negative 6 pascals is the pressure. Now, number density involves molecules per cubic meter. And as we think about that in terms of the variables that are used in our equations, we realize that that's N, capital N, rather, divided by volume. So as we think about what equations have we been using in this subject so far with ideal gas law, that would involve N over V. You think of PV equals NKT. Now we can use that equation and find what N over V is. N over V is P over KT. So then we plug in the pressure, K, which is Boltzmann's constant, and the temperature. Remember, you cannot use temperature in Celsius. You have to do the absolute temperature, which is going to be 293 Kelvin. And here's our answer, 3.296 times 10 to the 14th. Now, you see the answer, you see those dimensions are in pascals per joule. So it's good, those are kind of awkward units, not what we're used to. And we know that we're expecting molecules per cubic meter. So let's satisfy ourselves that pascals per joule is the same as molecules per cubic meter. So let's do some dimensional analysis. Pascals per joule, and I don't know if you can see this on the video, but I have pascals in blue ink and joules in black ink. So the pascals break down to newtons per meter squared, and joules are newton meters. And so the newtons per meter squared divided by newtons meters, newtons divide away, and you have 1 over meters cubed, which really is molecules over meters cubed, because like radians, molecules is not really a unit. It's what I'll consider here a pseudo-unit. Then in number 56 it says for part B, compare your results with the number density under standard conditions computed in example 12.9. So if you do that, going back to example 12.9, you have 3.3 times 10 to the 14th molecules per cubic meter. I'm sorry. Let me back out of that. That's not the comparison. That just is the final answer. The comparison, part B, I leave for you to do on your own. Number 60. For chapter 12, number 60, we have a compressed air cylinder standing 100 centimeters tall. So that's 1 meter is the height. And its diameter is 20 centimeters, so let's call its radius 0.1 meter. And it'd be good to know the volume, so use the volume of the cylinder, pi r squared h. And there I solve for the volume. It'd be good to know the temperature. It says room temperature. So let's use 20 degrees Celsius, which is 293 Kelvin. And it says a pressure of 180 atmospheres, which you should convert to MKS units, 1.82 times 10 to the 7th pascals. Part A is asking how many moles of air are in this cylinder. So moles is lowercase letter n, so it's appropriate to use PV equals nRT. Solve for n equals PV over RT. And what we get is 235.2 moles. Part B. What volume would this air occupy at room temperature and 1 atmosphere of pressure? Now, here's a neat little trick, and this will come up throughout the rest, some of the rest of these homework problems. There are different ways of solving this one, but let me show you something interesting. We can look at PV equals nRT and separate it into the components that are varying and the components that are constant. And what I mean by that is, if you read the question, it says what volume would this air occupy at room temperature and 1 atmosphere of pressure. So they're changing the pressure on us. Now they're asking, forget about 180 atmospheres, what about if we change the pressure to 1 atmosphere? And we know volume is going to change because the question is asking what would the volume be. Well, temperature is not changing because it's still saying room temperature. R is a constant, that's not changing. No gas is leaking out or coming in, so N isn't going to change. So we have the things that are varying on the left and the things that are constant on the right. So what we can then say is that if pressure times volume is equal to something constant, in this technique I'm about to teach you, we really don't care what that constant is, just to know that it is constant. So here, pressure times volume equals constant. And if pressure times volume is constant, then we can say this, that pressure at state 0 times volume at state 0 equals pressure at state 1 times volume at state 1. And so we're relating pressure times volume at one state versus another, and we really don't care about nRT anymore. We just care that pressure times volume is constant. Now, we can then solve for volume of 1. So volume 1 equals P0 over P1 times volume 0. When we plug in, the P0 over P1 is 180 atmospheres divided by 1 atmosphere. Notice I don't need to change that to MKS units of pascals because those units are going to divide out. What's in the parentheses is just a ratio of 180 to 1 times the original volume, which we solved at the top. So what we then get is a volume of 5.65 meter cubed, or cubic meters. Now, without doing that technique, another solution would have been just to solve directly for volume 1 equals nRT over P1. So the n that we solved in part A times R times T divided by 1 atmosphere, which in this case we do need that atmosphere in pascals because we're dealing with MKS units that are going to divide and multiply. And in that case, we also get the same answer of 5.65 cubic meters. Problem number 65. Find the RMS speed of hydrogen H2 at 273 Kelvin. Okay? Well, H2, we need to recognize from a periodic table that its mass is 2 atomic mass units. Later on in the problem, we'll have to convert that to kilograms. VRMS, here's an equation that's given in the book that I gave you in class, but let's do something interesting with it. Let me derive for you more convenient formula for this. That N over V, we solved for it in class. We used PV equals NKT, and we solved for N over V and got P over KT. And again, we did this in an example in class. So when I substitute n over v for p over kt, there's my p over kt, the p's will divide out. And this right here, that my pen is pointing to, is a much more convenient equation for the root mean square speed. Square root of 3kt divided by m. So that's a good one to tuck away in your notes to save for when you need it. So we plug in what we have. 3 times k, that's Boltzmann's constant, times temperature. You must use the absolute temperature, and that would become apparent if you tried to use Celsius and you plugged in 0, and the whole speed would go to 0, and then you should recognize something's wrong. So let's use 273 Kelvin divided by, the mass is 2 atomic mass units, but here it's appropriate. We're going to need MKS units. So do that conversion where an atomic mass unit is 1.661 times 10 to the negative 27 kilograms. What we get is the root mean square speed of 1845 meters per second. Now, in question B, question B is asking how much does the root mean square speed change if we change the temperature. Let's do this really neat technique. Let's set up a ratio of V1 over V0, which is square root of 3kt1 over m divided by square root of 3kt0 over m. Little bit of algebra here shows that the 3's, the k's, the m's are all going to divide out. What you're left with a bit of algebra, is where my pen is pointing. It comes out simply to square root of T1 over T0. Now when we recognize that the temperature has doubled, we can make a substitution that T1 is really equal to 2 times T0. So instead of square root of T1 over T0, we get square root of 2 T0 over T0. The T0's cancel out, and we get square root of 2. So what that leaves us with is that the ratio of the speeds, V1 over V0, is equal to the square root of 2. Now it's a simple matter, once we've gotten this far, just to see how much has it changed. So V1 is square root of 2 times V0. We solved V0 in part A. And so we should get that it's 2609 meters per second. The question isn't asking what is the new speed, but rather how much has it changed. So change in V is V1 minus V0, which is 764 meters per second. Number 69. Similar to the last one, we should set up a ratio V1 over V0, square root of 3kt 1 divided by m over square root of 3kt0 divided by m. Similar to how we did in the last problem, we do a little algebra and we get that it's the square root of T1 over T0. Very important here that you use not Celsius but Kelvin, those absolute temperatures. Square root of 353 over 293. And it comes out to square root of 1.2048 or 1.098. So we get that the new speed, the RMS speed, is 1.098 or a 9.8% increase over the original. And the last one, number 75. An ideal gas maintained at 1 atmosphere. By what percentage does the density change as the temperature changes? Okay, so we have original T 263 Kelvin, the final 305 Kelvin. This is a good problem in thinking about how do we relate concepts that haven't been given to us in the formula. Well, we know PV equals nRT, and you realize density isn't involved in that. But if you think, what do we know about density? Well, we know that density is mass divided by volume, for reasons that will become apparent in a little bit. I have here that volume is mass divided by density. And even though it's not readily apparent how this is going to fit in, just keep it off to the side and see what will happen. Use that technique I taught in an earlier problem, where we put all the taking PV equals nRT, put all the things that vary off to one side and all the things that are constant off to the other. So here I have on the left-hand side, temperature over volume. Temperature is varying. Since it's telling us that density is going to change and density is related to volume, you can figure volume is going to change. The things that are constant are pressure, because it says that's being maintained at 1 atmosphere. I want you also to notice that nowhere in this problem am I ever going to use the fact that it's 1 atmosphere. I'm only using that it's constant. N is constant and R is constant. Well, T over V. Now it's a good time to invoke what I wrote earlier, to off to the right, that V, volume, is equal to mass over rho. So T rho over mass is constant. But mass is constant as well. So if we multiply both sides of this equation by m, we get T times rho equals some other constant. I don't really care what that constant is, just to know that T times rho is constant. And if T times rho is constant, then I can say T naught rho naught equals T1 rho 1. Solving for the change in the ratio of the densities, R1 over R naught equals T naught over T1. Plug in those temperatures and we get 0.862, which means that the new rho, or rho 1, is equal to 86.2% of rho naught. Well, the question is asking, for number 75, by what percentage does it change? Well, if it's 86.2% of the original, 1 minus that is 13.8%. So we can say that it's down by 0.138, or it's a 13.8% drop.